us today at the second webinar of our underground storage and utilization technical community sponsored by the American Rock Mechanics Association. Markus Pichler is our speaker today. He studied petroleum engineering with a specialization in reservoir engineering at the University of Leiden in Austria. Before finishing his master's degree, he joined the underground gas storage team of RAG in 2012. His work includes planning and developing underground gas storages, as well as customer service. Additionally, he is working for the Green Gas Technology Department as a senior researcher in the topics of geochemistry, and hydrogen infrastructure. Since 2018, he has also been responsible for the production and development of gas fields. Of Marco Gas, SPE, and OVGW, he regularly speaks.
Richard, thank you for the introduction. So there's nothing more to say about my person. Good afternoon, good evening, good morning, wherever you're sitting. And I think we go ahead. So today I want to talk about our underground storage project, which we did in all, but a bit of advertisement about my company. I should go ahead. Yeah. So RAG Austria is among the leading underground gas storage operators in Europe. We have a storage volume of about 60 assets. As you can actually see that we want to use assets in a renewable energy future. And as an operator, we thought about how we participate in such a renewable energy future. And the logical choice here was gas, and this gas being hydrogen, which is generated by the power-to-gas technology. So why exactly hydrogen should be clear when we look at this picture, because as a difference to electricity, you can store hydrogen in huge amounts within geological formations. And this is one of the reasons why we were looking at hydrogen, because we would need huge amounts to get the energy when it is generated in summer or during the windy seasons in fall to the winter where we really need it. And as you can see, huge volumes are needed in this account. But additionally, as we are connected to the European gas grid, okay, sorry, now it's working. The European gas grid is connected to the most promising areas of renewable energy generation within Europe. And in Europe, we're developing a huge hydrogen infrastructure, and all these electrolyzers, they want to put their hydrogen into the gas pipelines. So at some point, all the storage operators in Europe will need to deal with the hydrogen. I put here the European wind map with the gas network of Europe, and I as well have here the European sun map as well with the same gas grid. So you can see we can't close our storages for the hydrogen. We will at some point have to deal with it. And RAG wanted to take the lead in this and said, okay, we're looking now at our reservoirs and how would those reservoirs react to hydrogen getting into it. So in 2013, we assembled a high-quality consortium of academia and energy companies to exactly answer the question of what would happen if we would inject a mixture of 90% of natural gas and 10% of hydrogen into our reservoirs. But we didn't want to just answer this question on lab scale, but we wanted to test it on a pilot scale, which is why we actually developed one of our reservoirs, very small reservoir, I come to this in a second, to an actual test bed facility where we could test this in the field to get a feeling not only what happens in the lab, but what really happens outside in the field if we injected hydrogen. As you can see from the work packages here, just shortly talk about them, we really wanted to cover each and every angle of the storage technology as such, to really have an idea, okay, what happens to materials, what happens to the reservoir, what happens with the microbes, as well as what do we look at in economic, in an economic point of view, as well as legal point of view. So I just want to shortly to introduce our reservoir. It's a very small reservoir, as I said that. It's very isolated. There are a lot of offset wells around the reservoir which do not penetrate the same horizon. You can see alone from the volume, it's just about 6 million cubic meters of volume gas initially in place, that it is really, really small. So it was only found by chance, not really drilled upon. But it is the perfect test bed. It has a very low pressure, very low temperature. So you could really do a lot there without having to invest very much. And the next positive thing is that these conditions we're speaking about here, and I'm just speaking about the geological and the reservoir conditions, are comparable to our commercial storages. Sorry. So just to give you an idea where we are stratigraphically, I just let that stand here. So as you can see, it's a secluded reservoir. There is nothing around there, nothing below that. And sorry, could you please mute devices? Thank you. And just another positive thing is there is nothing above. So I plotted the completion log here, and you can see there are no sand layers or whatever above the sand layer we are speaking about. So therefore, someone is has still his device on. Richard, can you mute them remotely?
I will see what I can do.
Okay, I'll go ahead then. And this was very important for us to have a really secluded reservoir in order to do whatever we want there without risking any other facilities, without risking anything at the surface. So what we wanted to do on a technical point was to answer the most relevant questions from the literature, being, do the different materials of the gas storage facility have a problem with hydrogen? Because as you can see, we didn't want to build a new facility for hydrogen. We wanted to use our in situ facilities that we have there. And so we wanted to make sure that they can deal with hydrogen without any major modifications. The next thing, naturally, is the tightness of the subsurface. Would hydrogen escape through the caprock, through the completion? The next thing was, how does the gas mixture move in the subsurface? This was especially important because the molecules of hydrogen and CH4 have a different size, so you could end up with some dispersion flow where the hydrogen moves faster than the CH4 through the reservoir, which then in the end would mean that you would reproduce a non-uniform gas mixture, which is not very nice for the end customers which want to have a uniform mixture. Finally, does hydrogen change the chemical equilibrium as well as the biological equilibrium in the reservoir? So are there any reactions in the subsurface that would be harmful for the facility or that would lead to a major loss of hydrogen? Starting with materials, we tested the metals, the elastomers, as well as the cements that we use outside in our facilities in the laboratory for their resistivity against hydrogen-induced changes. We found that the steel grades, as well as the cements we use outside, did not change during the lab experiments. So we put them under strain stress tests with a partial pressure of hydrogen up to 150 bars. The cements were submerged in reservoir water and then exposed to hydrogen for almost a year. There were minor changes, as you can see in the picture. A reaction seam developed where the vaterite of the cement changed to calcite, which is, however, something that happens due to the reservoir water. So we did also do the same test with blind samples without hydrogen, and the changes happened with and without hydrogen. And finally, we had a look at the elastomers. However, we didn't test the elastomers in the lab yet. that will be done in a follow-up project. We just tested them outside. You can see a picture of our test pipe where we submerged cement samples, steel samples, as well as elastomer samples within the wet gas stream throughout the whole project, and then measured the changes of those samples at the end of the project. And we found that the same changes that happened in the laboratory, speaking of none, also happened outside. There were minor increases in mass and volume with the elastomers, but they were within gas industry standards. So speaking of, if you would inject just CH4, you'd see the same changes in the elastomers. And to mention it, in the follow-up project, we already are running a follow-up project. We do a closer investigation about these elastomers to really be sure that no hydrogen-induced changes happen. I'll head further into the reservoir, and I already said that we tested cement steel grades as well as elastomers. The completion you can see here was taken out after the field test was finished and sent back to the manufacturer, and they told us after testing it that it looked like new. So no changes happened at all to the completion which was used during the test. We also ran a CBL and the USUTC before and after the testing in order to get an idea whether corrosion would happen or whether the hydrogen would migrate through the cement behind the pipes, and both came back very positive. So we saw no corrosion, no changes in the casing, and no micro annulus in the cement behind the pipe. But speaking of reservoir integrity, there is not only the wells but also the cap rock. For our reservoirs, the cap rock is just a clay rock, so no salt, no anhydrides or something, but just clay. And we tested the permeability of the clay for methane and for hydrogen. You can see this in the table below. And you can see that the permeability for hydrogen and methane is in the same order of magnitude. So we decided for us that if the cap rock was able to keep methane, it would also be able to keep hydrogen. Therefore, as permeability was the same, we had to think about diffusion through the cap rock, and there is a lot of literature about hydrogen diffusion through porous media. And you can see, I wrote it at the top, that hydrogen diffusion in water-saturated porous media is just very, very low and not relevant if we're speaking about gas storage, because I won't keep the gas down there forever. It's just down there for about a year. So therefore we said, okay, for us, the diffusion through the cap rock is not an issue, because our cap rock is 100% water saturated, and therefore we concluded it's not an issue. However, diffusion could also lead to the demixing of the gas, which also would end up us giving a non-uniform gas mixture coming out of the reservoir. And so we tested whether or not the gas would change, the gas mixture would change due to gravitational forces. So we put a gas mixture of CH4 and H2 into a steel pipe 7 meters long, filled with sand, and let it stand for 1 year, and took regular samples at the top and at the bottom. You see this in the left upper corner, and to investigate whether or not there would be some gravimetric demixing. And you can see there isn't. So we were pretty sure that in the reservoir there wouldn't happen any kind of demixing, because diffusion forces apparently are stronger than gravitational forces. However, as you can see from the graph in the left lower corner, when we produced the hydrogen, the mixture wasn't anymore uniform. So the injection was with 10% of hydrogen. The production was slightly decreasing. And so we asked the question, okay, what happened to the reservoir? So we could, to the hydrogen, pardon. We could reproduce 82% of the injected hydrogen. And the first thing we said, okay, so some of the hydrogen must have diffused into the cushion gas. So there was still some gas inside the reservoir, some natural gas inside the reservoir. But this couldn't be the whole story. So we thought about what else could have happened to the hydrogen, and came up with dispersion, dissolution, chemical reactions, as well as conversion. I'll just stick to diffusion for a moment. After we finished the field test in 2017, we, 1.5 years later, we took another gas sample in the same reservoir, and it still contained 1% of hydrogen. So this made us sure that the cap rock is tight against hydrogen migration, and as well that there are no sudden chemical or biological reactions that would have in any way reduced the hydrogen or expunged it totally. So we were pretty sure that the hydrogen was tight, that the reservoir was tight, and that the hydrogen didn't react with anything in the reservoir. But we did further testing, first for dispersion, because as I told you at the beginning, there is literature about saying that hydrogen and natural gas move at different speeds through the reservoir. We took again our 7 meters long sand-filled pipes and sent hydrogen and CH4 through it to measure breakthrough times. In a dry environment, the breakthrough times were different. So the hydrogen was always slightly faster than the methane. However, when we then later water saturated the sand pipes, this effect cancelled out. And so we concluded that at least over short distances, methane and hydrogen are traveling with the same speed throughout the reservoir. So we ruled out hydrogen doing some kind of viscous fingering and therefore getting this slope. Next was dissolution. If you read in the literature, you get a really, really broad number of how much hydrogen could dissolve into reservoir brines. So I'm speaking about 0.9% to up to 10% of the injected volume. We saw in the lab, this is this graph here, that hydrogen does dissolve into the water, and if you reduce the pressure, does come back out again. But we really couldn't fix a point where you could say, okay, so much hydrogen will dissolve in our reservoir water. And as all reservoir engineers know, to get an idea of how much water is in the reservoir is also not very easy. So having the connate water as well as the aquifer water, and therefore, in the end, we have two unknowns. We don't know how much water is there, and we don't know how much will dissolve. So this is one of the major findings we had from the sand storage reservoir to say, okay, we have to look at this more closely, and we also have to look at kinetics in order to know how much does dissolve and how much does stay in the water, because this number has to be known before making a commercial hydrogen project. And we're investigating this as we're speaking in our follow-up project. And then again, we came to reservoir changes. So hydrogen is very reactive at the surface. We know that it happily reacts with oxygen. And there were also some thoughts about what could happen in the reservoir and with which materials could the hydrogen possibly react in the reservoir. Therefore, we again started with lab tests where we took cores from similar formations and again submerged them into reservoir water and then exposed them to 25 and 75 volume% of hydrogen up to a pressure of 120 bars, and kept those samples in the reactors at reservoir temperature and reservoir pressure for 2, 3, 6, 9, and 12 months and measured the changes. Even at thin section level, we couldn't find any changes. So the permeability did change, but also in the blind samples. And after some investigation, we found that the error we made was that we used very old cores that were dried out, and exposing those dried cores again to water led to clay swelling, which then in the end changed the permeability. We also investigated the permeability of our reservoir with doing well tests on a regular basis. You can see this in the on the left bottom corner. And the permeability did change in the reservoir. However, it didn't change dramatically. Because these changes you can see here, they are the same changes that you see in each and every gas storage if you open it up. Because due to injection, withdrawal, you clean up your perforations, and then again you're injecting dry gas, you're withdrawing wet gas, then again injecting dry gas. You also dry out the near wellbore region. Therefore, the permeability has to change. And in the end, when we finished the test, we reproduced all the gas until the point the well watered out, and then again the permeability changed. So therefore, we concluded that the hydrogen has no effect or no measurable effect on the reservoir rock for our conditions. I have to say this again, these are very nice conditions, pressures only up to 100 bars and temperatures only up to 40 degrees. And last but not least, there is the conversion. So most of you might know that a lot of the gas we are producing worldwide is not of thermogenic but of biogenic origin. And the microbes which have generated this gas are still in the subsurface. They're still in the source rock, they are still in some of the sand layers, and obviously they were still inside our test reservoir. And when we injected the gas mixture, we also had some amounts of CO2 within the natural gas. And as you can see at the end of the field test, the CO2 was almost gone. And we found that this conversion must have been of biological origin, because if it would have been of chemical origin, then we would have seen some changes in temperature, and I therefore plotted the temperature plot here. You can see there is some minor change in temperature, but this is just because you're injecting cold gas and withdrawing warm gas. And therefore we deduced, and I'll give you a second slide in a second, that the effect that we have seen here must be of biological origin. Positive for us was that these were the only reactions we saw with hydrogen, so we didn't encounter any H2S, although we have sulfur sources within the reservoir, being SO4 in the reservoir brine as well as pyrite in the rocks. We also didn't find any evidence of iron reduction. We found small traces of acetate, but they are natural to the reservoir. So therefore we concluded that this can only be an effect of the microbes that can convert hydrogen and CO2 to CH4. We then tested this in the lab, and what you can see on the next slide is exactly the outcome of this test. So on the leftmost side, you see the microbial at the beginning of the test, where, and I want you to focus on the pinkish column. So at the beginning, there were almost no archaea within the consortium. And after we finished the tests, the archaea made up the majority of the microbial consortium, which we concluded was due to that we fed them, and we fed them for a long time. The reservoir was shut in for almost 4 months. And afterwards, the microbes had consumed all the CO2. And when the CO2 was consumed, they got back to dormant state and didn't consume any more hydrogen, but they grew dramatically. This is also something we would have to look at in our follow-up project, because if they grow further, they might even plug our pores. And finally, we also had a look at economics and legal analysis. I won't go too much into detail here. If you have questions here, I'll take them with me. I'm happy to take them with me. But as I'm a technical advisor in this project, and economics and legals are not my strengths, I would forward those questions, if you have some, to the guys who really have an idea about that. So summing up, underground sun storage was a success. We could prove that 10% of hydrogen could be stored within our facilities, within our reservoirs, without changing anything and without any harm done to the facility or the reservoir. And we think that we identified a key parameter for a renewable energy future, where you could really store huge amounts of renewable energy in a safe way and provide it to customers and to the industry if needed. I'll just have 3 more slides about our follow-up project, and I just want to go through them very quickly, because there were a lot of open questions. I mentioned them throughout my presentation, and we wanted to answer them as being the diffusion. We wanted to know, does the diffusion have a further effect in the reservoir? Dissolution, I talked about that, we're already investigating it. Microbial activity, we're also investigating it. Modeling was also something we found out. There is, at least to our knowledge, no commercial software developed yet that can readily simulate the behavior of hydrogen in the reservoir. Then there were the rubber seals and the elastomers. We're also looking on them in the follow-up project. And the movement of hydrogen is not yet clear for us. even if what we saw is true, we still want to know more. And we also do this in our follow-up project. And speaking of which, this follow-up project is called underground sand conversion, where we want to utilize the conversion effect that we saw. So we want to know if the microbes are able to convert hydrogen and CO2 on an industrial scale, because if we could make this work, then we would convert our one-way industry into a sustainable carbon cycle industry, where we could keep our facilities as they are, as we would just keep producing CH4, no changes for the end customers, no changes for the industry, but still doing it with renewable gas without having to build huge methanation facilities on the surface. This project started in 2018. We're already doing the third batch, where we inject hydrogen and CO2 and reproduce it after a certain shut-in period. I'm sorry that I can't present any graphs to you yet, as this is ongoing work, but there will be a final report in mid-2021. And everyone who gives me a hands up will get the report then, and I will tell you where to get it. Yeah, just a quick note. So the idea of this project is really to push further the idea of how much can these microbes convert, how much volume can they convert, up to which mixture could we inject hydrogen and CO2 without getting any harmful effects within the reservoir. And as well as how does the biomass in the reservoir react? Do we get clogging? Do we get any other issues? Do we get any other reactions due to other microbes being activated? So that's the idea of the second follow-up project, where we are now fully engaged. And as a conclusion to all of this, I want to say that the state-of-the-art underground gas storage facilities, in our opinion, will be an essential part of the energy security of the not only the Austrian energy security, but the worldwide energy security. The renewables need gas storage, they need energy storage due to their fluctuating nature. And we think that with our sun storage and sun conversion project, we have really laid a very, very good foundation to emphasize that we could use the renewables not only as electricity, but to make up a whole new part for the renewables in injecting them into the gas grid and using them as gas for the right application. And with this, I'm finished with my presentation. I thank you very much for your attention, and I hope there are a lot of questions. Thank you very much. Oh, there is now one. Is there microseismicity associated with the underground storage, or are injection pressures low enough to be of concern? Well, thank you for this question. Actually, there is no issue. So the region we have our gas storages in is called the Molas Basin. It's in Upper Austria, and it's absolutely non-active in any way seismically. And we're only injecting up to initial pressures, so being pressures that the overburden has already seen. So there are no, we didn't measure any events or any faults being reactivated or whatever. Oh, the hydrogen, we produced it via electrolyzer. Thank you for this question. We had an electrolyzer unit on the facility and produced the hydrogen from that. So the next question, thank you for that one. What is the energy conversion efficiency in the system? In other words, what is the energy recovery rate? Well, that's a tough one to answer because we think we're still in a dynamic environment, and the equilibration of hydrogen in the reservoir has not yet been fully happened. As I told you, 82% of the hydrogen could be reproduced, and that's where we're standing at the moment. So there will definitely be some losses within the reservoir due to the nature of equilibration. You just need to have an equilibrium in the reservoir of all the components before you can produce, inject and produce the same mixture at any time. I hope this answers the question from Jamal Ostami. I hope I pronounced this right. Then from Amjad Prasad, I hope I pronounced this right. I'm sorry if I don't. I joined a little late. So my question is very preliminary. The permeability is square meters. Okay, I can also tell you the permeability in millidarcy. It's between 1 to 1,000, 1,200 millidarcy. Oh, hi Helen. How are you? What is the social acceptance of the sun storage project? Well, the thing was that we were really open and transparent with this project. So we visited a lot of people in the vicinity of the storage facility previous to starting the project. We also were in contact with the authorities before even starting the project and got a really, really good acceptance levels. So basically no stones were laid in our way because all the people were really happy about what we were doing there, because it was a renewable project, and the area where we are operating, RAK is known there. So we are known there as an oil and gas producer. But now suddenly we came up with a renewable project, and this was we get a really positive resonance back from all the people in the vicinity, because they say, okay, yeah, you're changing, you're doing something, you're looking to the future, you're not just an oil and gas company anymore, but you really want to do something with renewables. And so they really were happy about it, and they engaged us in discussion. We did, for example, we did regular workshops at the facility where we showed the people what we're doing and what our plan is for the future. And they really all, so there was even a farmer in the vicinity who regularly brought cake during the construction phase of the facility. So really positive resonance, as well as from the authorities. So from Ganghan, pardon for not being storage. Well, yeah, that's a difficult question. Thank you for that one. I really think looking at steel manufacturers, looking at Siemens, on all the energy-intensive industry we want to keep in Austria, I don't see another option. If you would want to just sustain them with electricity, you have a windmill on every corner. You have to close every valley with a dam to produce the electricity. That can't be the way forward. In the end, you will need hydrogen for the energy-intensive industry, because it can be stored, it can be transported, it can be easier transported than electricity. These are the major benefits of it. I don't say hydrogen is the total solution. I think you have to look at the right energy source for the right use. But looking at energy-intensive processes, I'm pretty sure that we're in a good run with working with hydrogen. Next question from Mari Haddad, sorry. How much larger is the diffusion compared to methane in your reservoirs? Also a very good question. Thank you very much. Basically, due to the fact that hydrogen dissolves into the reservoir brine, so only 1/10 of the volume of CH4 that would dissolve into the reservoir brine does roughly dissolve as hydrogen, and this slows the diffusion process. So in the end, it's in the same order of magnitude, but I have no total number for you. I would have to look this up. Thank you, Richard, for this question. Well, we have actually done this. We have made a template. It's in our final report. If you go to the Underground Sun Storage homepage, I'll put the URL on the last slide of the presentation, and I also will share this presentation with you afterwards. And there you can find our final report. And one chapter is dedicated to exactly this question: how should another oil or gas company go forward? What research should they do, and what are the key factors they should look at in order to test their gas storage or their oil field for the feasibility of hydrogen storage?
like to ask Markus if he might have any closing thoughts, please.
Any closing thoughts? That's also a tough one. Well, again, I want to thank you for participating. I want to thank you for giving me the opportunity to speak on an international level. As I told Richard in the beginning, the hydrogen storage and the use of hydrogen is quite young. And in order to really get this going, and in order to get it into the heads, not of only us scientists, but also of decision makers of big companies, we have to share our knowledge. We have to share of what we have done in order to make people see, okay, there is a hydrogen as well. Everybody is talking about electricity, but electricity is only part of the solution, as hydrogen is only part of the solution. And in order to make a renewable energy future happen, we need to look at each and every idea that comes up and verify whether it is a good one or a bad one. But we should not close our eyes for new ideas. We should not just search for one solution, but look at every solution that is out there.